In our last video, we talked about how we can use rectangles to approximate the area beneath some sort of a curve. We defined these sums, Rn, to be the approximation of the area by n rectangles. And just to refresh you, we're going to draw the three pictures that we had from our last video down below. So here we have R1, R2, and R3 for the function x squared bounded between 0 and 1 along the x-axis. So we did this construction for 1, 2, and 3 rectangles and a single function. But what we really want is a way to systematically describe rectangles for any function. So to do this, we need to be able to describe, first of all, the bases of our rectangles. So we're going to start with the following setup. So the setup is we have a continuous function f and a closed interval a to b on which f is defined. We're interested in measuring the area of this shaded blue region, which is bounded on four sides by the function f, the x-axis, the vertical line x equals a, and the vertical line x equals b. In the previous construction, we decided, first of all, how many rectangles we wanted to use. And we cut the region from 0 to 1 into as many pieces as we needed rectangles. Those parts of the x-axis formed our bases for our rectangle. So if we're going to do this in general, we need a way to first of all create our bases. So the first thing we need to know is what the width is. So to construct n rectangles of equal width, we're going to cut the interval AB into n pieces of width b minus a over n. The reason for taking b minus a over n is that we want to create n rectangles. We want all of the bases to be the same width. So b minus a in the numerator here represents the width of our interval, while n represents the number of pieces that we want to cut it into. So here we can see the stretch from a to b along the x-axis, and you can see that we have cut this into n equally sized pieces, each of them having width delta x. We're going to call each of these pieces a subinterval of a to b, and we're going to number them from left to right. So you can see here, we've given each of these pieces a name. Since they're a subinterval, they are in particular an interval, so their names are all I, but they're numbered to distinguish them. The first one is I1, the second one is I2, the third one is I3, then I4, and we keep going along until we get to IN minus 1, and finally IN. Now, since each one of these is actually an interval, our intervals have to be specified by endpoints. So we're going to label these points from left to right with a numbering. The first point is going to be x0, and that is a. Our last point is going to be xn, and that's b. So now that we have our numbering, we can see that we start with x0, which is the left endpoint of the first interval. Then x1 is the right endpoint of the first interval, but also the left endpoint of the second interval. x2 is going to be the right endpoint of I2 and the left endpoint of the third interval. x3 will be the right endpoint of the third interval and the left endpoint of the fourth interval. x4 will be the right endpoint of the fourth interval. We keep going this way until we get to the n minus first interval, whose left endpoint is xn minus 2, and whose right endpoint is xn minus 1, and then in, whose left endpoint is xn minus 1, and whose right endpoint is xn, which is also our right endpoint for our original interval, which is b. So this gives us a way to describe each of these subintervals. So there's an important pattern to recognize here. If you want to write down the ith interval, then you need to take the points xi minus 1 as your left endpoint and xi as your right endpoint. So for each one of these, whatever your index is on your interval, so the first interval, your left endpoint is an x with its index 1 less than that of the interval, while the right endpoint maintains the same index as the interval. Same with 2. The second interval has left endpoint x1, right endpoint x2. So I'm going to highlight that just to really point this out. Now here, b, it's important to note, is the same as xn. Now that we have a way to describe each of the intervals, we would also like to be able to describe each of the points. Because if we can describe the points, then we can describe the intervals, and if we can describe the intervals, then we can describe the bases of our rectangles. So we're going to think about describing each of these points relative to A. So first and foremost, we're going to start with a picture, and we'll start to fill it in. The way this works is we have a starting point. That's A. We can describe how to get to each and every one of these points, x1 through xn, by thinking about how many times we move by delta x. So to describe x1, we think about that as being 1 delta x away from A. To describe the point x2, we know that x2 is 1 delta x away from x1, which is 1 delta x away from A. So we can describe that directly as being 2 delta x's away from A. Similarly, x3 will be 3 delta x's away from A. x4 will be 4 delta x's away from A. And so in general, if we want to describe the point xi, then that point is I delta x's away from A. And we keep going until we get to xn. And we note here that xn is supposed to be b. So to make sure that our system actually works, we're going to check to see that we really do get b for xn. And so we can see that we end up at b as we wanted. So just to make this really clear, I'm going to highlight my indices and my multipliers. I'm going to also throw in a 1 on the very first delta x, just to make this really explicit. So now that we know how to describe the way to construct the bases for our rectangles, we're going to give this a name because it's very important and it's going to keep coming up as we move through this unit on integration. So now that we have this new word, let's go back to our old example where we had the interval from 0 to 1, and let's compute a couple of different partitions. So first, we're going to partition the interval from 0 to 1 into 2 subintervals. The first thing we need to do is figure out how wide each of the 2 subintervals are going to be. So we take b, which is 1, we subtract a from it. That gives us the length of our interval, which is, in this case, just 1. And we divide it by the number of subintervals we want to make, which is 2. So the next thing we need to do are determine our points. So our first point is easy. That's just 0. Our second point, x1, is 1/2 of a unit away from x0. That's x1 is 1/2. And our second point, x2, is 1/2 of a unit away from x1, or twice 1/2 a unit away from 0. So since we are subdividing into 2 intervals, we need 3 points, and these 3 points give us the endpoints of our 2 subintervals. So we're going to write down our subintervals I1 and I2. There we go. Those are our 2 subintervals. And we can draw them also, and they should correspond exactly to what you would expect. There you have it. You just cut up an interval of length 1 into 2 pieces. You get 2 intervals, each one having length 1/2. There is our partition with n equals 2. We could do this again with 4 as our second example. Again, to partition our interval from 0 to 1 into 4 subintervals, we just need to compute the width of each subinterval. That's our delta x. Compute the points, and then write down the actual intervals. So when we partition into 4 subintervals, then we should expect the width of each one to be 1/4 of the length of the total interval. Next, we want to write down our points. So again, we start from the left endpoint, that's 0, and we call it x0. Our next point is 1/4 of a unit away from x0. The next one is 1/4 of a unit away from the first, or 2/4 of a unit away from the original. Our third point is going to be 1/4 of a unit away from x2, or 1/2 a unit away from x1, or 3/4 of a unit away from x0. And our final 5th point here is x4, and that has to be 1. And you can check that 1 is indeed 4 times 1/4, so it's 4/4 away from x0, which was 0. Our 4 intervals are as follows. And just to make sure that all of this makes sense, we can draw out our picture. So you can imagine now that if you were to chop the interval from 0 to 1 into n pieces, each piece would be 1/n units wide, and you could describe each of the points, xi, as I multiplied by 1 divided by n. So now that we know how to partition the x-axis, we can construct the bases for our rectangles. And in the next video, we're going to talk about how to construct our heights.